Hello and welcome to a lesson where we will be solving systems with three unknowns. Now the process that we're going to be looking at could be applied to larger systems, but for the purposes of this class, a 3 by 3 is going to be sufficient. So three unknowns and three equations is what we were looking at. If we want to be able to solve a system that contains three unknowns, we're going to have three equations. And then the solution is going to contain a value for each of those variables or unknowns. And if you have a 3 by 3 system like the one we're looking at here, three equations, three variables, instead of an ordered pair, like we saw with the 2 by 2 systems, we have an ordered triple. So this ordered triple here represents the solution to the system, and the variables line up with the equation. So for example, if we see x first and then y second and then z third here, then the first solution here represents an x and the second solution represents a y, and then the fourth one represents a z. So if we saw a 4 by 4 where it was x, y, z, then w, you would have a solution with x and then y and then z and then w. So you're sort of writing them as a coordinate. It's not really a coordinate because it's obviously got more values in there than x and y. We could not graph that on a coordinate plane, but we're writing them in the same fashion. Okay, so what we're going to do here is, what are we asked to do? Verify that this is in fact the solution to this 3 by 3 system. Remember, a solution should make all of the equations true when you plug the variables into each of them. So let's plug this into, let's call this first equation, equation A. Let's plug into A and make sure we end up with the true statement. So an x, which is 5, plus 5 times y, which is -1, plus 5 times z, which is -2. This should equal -10. And so we have 5 minus 10. And the 5 and -5 cancel, and -10 does in fact equal -10. So 1 for 1. Let's look at the second equation. We'll call it B. For equation B, it says that x plus y plus z, so 5 plus a -1 plus a -2 should all equal 2, and 5 minus 1 is 4, and 4 minus 2 does in fact equal 2. So 2 for 2. And let's try this third one. I'm going to call this last equation C. If we plug into C, we've got an x, which is 5, plus 2y, so 2 times -1, plus 3z, so 3 times -2, and that should all equal -3. So that's 5 minus 2 minus 6. 5 minus 2 is 3, and 3 minus 6 does in fact equal -3. So when you plug each of the variables into each of the equations and the resulting statements are all true, you have to have the solution to your system. Okay? So how do we solve a 3 by 3 system? So given a solution, verifying, no big deal. But how do we start with the system and figure out what that solution is supposed to be? The goal would be to use our process of elimination. So the elimination method, or sometimes called the addition method, is where you're adding the equations together to get rid of a variable. The goal is going to be to take a 3 by 3 system and use elimination to get it down to a 2 by 2. So we're going to start with this 3 by 3. We're going to use elimination to get down to a 2 by 2, and then the 2 by 2, we've got options for solving. We could use elimination again, we could graph, we could use substitution, but elimination is going to work pretty well here, so we can continue with that method. So how do we start with a 3 by 3 and get it down to a 2 by 2? What we want to do is choose two of the equations to eliminate a variable. Doesn't matter what two equations you choose, and it doesn't matter which variable you choose, but you do want to be strategic. So whatever looks easiest to get rid of. So for instance, if I was looking at this system, adding the x and -x together, I don't even have to multiply an equation. I might start with those two. Okay, but let's start with number 1 here, okay? We're going to choose two equations to eliminate a variable. Doesn't matter which two equations, doesn't matter which variable. But just so that we can stay organized here, I'm going to call this equation A, and this equation B, and this equation C. So if I want to pick two equations and eliminate a variable, again, doesn't matter, but all of these start with a 3x. If I can just make one of them negative, then getting rid of the x's would be pretty easy. So I'm going to, let's say I multiply equation A. So I'm going to do B minus A. Multiply equation A by a negative, and then add b to it, or take b and subtract a, and this is going to be to eliminate x. Okay, so b minus a to eliminate x is going to be my first step here. You don't have to write your steps out every time, but I'm going to try to show you how I organize the work, and hopefully that will help you in this process too, because the organization, honestly, it's the key to doing this, because the work isn't hard, but it becomes a big jumbled mess if you're less organized. Okay, so we're going to take equation b. Oops, that's my eraser. Equation b was 3x minus 2y plus 2z equal to 14, and I want to subtract a, so a is going to be multiplied by a negative. If I took a and multiplied this whole equation by a negative, if I subtracted everything in the equation, then I'm looking at a negative 3x, and then a negative y, and then a negative z, and then a negative 6. So make sure you get both sides of the equation there, okay? So all of that multiplied by a negative 1 gives me the result here. Actually, I could leave that there. And now I'm going to combine these equations. And when I combine them, what happens is the x is eliminated, which is what I wanted to happen. So those go away. I'm left with negative 2 and negative 1, so negative 3y. 2 minus 1 is going to be 1 left in front of the z, and then 14 minus 6 leaves me with 8. And I'm going to call this new equation that I came up with here equation D. Okay, so that is one equation with two variables. So step 1 is done. I picked two equations and I eliminated a variable. So now what I need to do is choose two different equations. So I started with a and b. In the next step, I can use a and c or b and c, just not a and b again. Two different equations, but I want to eliminate the same variable. So two different equations, but eliminate the same variable. So I can do something similar, like I could do b minus c, or I could do a minus c, or c minus a. I just need to make sure it's two different equations. So I'm going to go b minus c to eliminate x again. So two different equations, but eliminating the same variable. All right, so b minus c. So b is coming down as is, 3x minus 2y plus 2z equal to 14. And now I want to subtract c. So c is going to be multiplied by negative 1, which is going to make it a negative 3x, a negative 3y, a positive 3z, and then a positive 6. So distributing that negative, negative there, positive there, positive there. Okay? Get rid of all this ugliness. Okay, so now when I put these two equations together, what happens is x goes away. That's what I wanted. Negative 2y and negative 3y gives me negative 5y. 2z and 3z gives me 5z. And then 14 and 6 leaves me with 20. And I'm going to call this new equation that results here equation E. Okay? So what I'm left with now, these two remaining equations that I just ended up with here, that's a 2x2 system. Now I have two equations with two variables, and I can use elimination again. Okay? So I took my 3x3, eliminated x's, to end up with a 2x2. So the resulting equations, D and E, gives me this 2x2 system, and I can use elimination to solve this 2x2, the same thing that we did in the previous topic. So now, if I want to use elimination to solve with this guy here and this guy here, with D and E, I think the easier variable to eliminate would be the z, and so I'm going to take equation D, this equation here, and I'm going to multiply it by a negative 5, so that the negative 5 in front of the z and the positive 5 in front of that z are going to cancel. So just so I can again be organized with my work, I'm going to label exactly what I'm doing here. So I'm going to take E and subtract 5, or combine 5d. So negative 5 times d plus e, or e minus 5d, same thing. And this is to eliminate, too sloppy here, e minus 5d, and this is to eliminate z. Okay, so E is negative 5y, positive 5z, and 20, and negative 5 times d. So I'm going to take d, and I'm going to multiply it by negative 5. That's going to give me positive 15 in front of y, negative 5 in front of z, and then negative 40 on the other side of the equal sign. So now if I combine these two equations, z's are gone. That's what I wanted to happen. And then negative 5 and 15 leaves me positive 10 in front of y. And 20 minus 40 gives me a negative 20. And now I'm down to one equation, one variable. So now I can solve for the one variable and use back substitution to finish this out. So if I let me see. If I divide both sides by 10, then that's a really ugly color, sorry. Y is going to equal a negative 2. So now I use back substitution to solve. So now that I have a value for y, I can plug back into either d or e, or actually I have those here too, d or e, to figure out z, and then once I have y and z, I can plug into either a, b, or c to figure out x. So it's back substitution. Okay, so now I'm going to plug y into, it doesn't matter if you choose d or e. I'm going to just plug it into d. It looks a little simpler. So plugging y into d, I end up with negative 3 times negative 2 plus z equals 8. So that's 6 plus z equals 8. And subtracting over that 6, use this bad color, subtracting over that 6, then we can see that z is going to be 2. Okay, so there's that. I got y, I got z, and now I need to plug the y and the z into either a, b, or c. So now I'm going to plug y and z into a, b, or c. It doesn't matter. I'm going to go with a. It has less coefficients. Okay, so I'm going to plug into a, and maybe just as a note here, or e could have been used. Okay, or b or c could have been used, but I just chose a. Alright, so y and z gets plugged into a. So a, we have 3x plus y, which was a negative 2, plus z, which was a positive 2, and that has to all equal 6. So positive 2, negative 2 cancel, leaving me 3x equal to 6, which means if I divide both sides here by 3, that x has to be equal to 2. So x equals 2. So x, then y, then z is my solution. So my solution is going to be the x, which was 2, the y, which was negative 2, and the z, which was 2. It's a lot of 2's, okay? But there it is. That is my solution to that system. And if I wanted to verify, I would plug that x, y, and z into all three equations to make sure I had true statements. Okay? So not terribly difficult work, but it is really important to make sure that you stay organized with that work. I'm going to try to scooch this over. Wouldn't it be nice if you could do that on yours? Huh? Just pick stuff up and move it over. Alright, just to make sure I have room for my next problem. And let me just go ahead and separate that. I hope this is going to be enough space. We'll see. Okay, so I'm going to change colors this time so it doesn't run into each other. Get off of that tool. Okay, so again, let's just organize. I'm going to call this equation A, this equation B, and this equation C. So I need to start by choosing two equations and eliminate a variable. It doesn't matter what we choose. So like it looks really easy to get rid of y's. It looks really easy to get rid of x's. It doesn't matter. Let's just choose. Okay, so last time I started by eliminating x. So I'm going to go and start with y this time. So what I'm going to do is I'm going to take A and add C. I'm going to add B. A and B together, if I just add these together as is, those y's are going to cancel. So A plus B to eliminate y. That's going to be my first step. So A is x plus y plus z equals 6. b is 2x minus y plus 2z equals 6. If I add these together as is, y's cancel. 1 and 2 leaves me 3x. Again, 1 and 2 is going to leave me 3z, and 6 and 6 gives me 12. So this is going to be equation D now for me. Okay? So I used A and B to eliminate y. Now I need to pick two different equations but eliminate the same variable. So I'm going to use B and C this time. If I just add these as is, y's will go away once again. So I'm going to take B, I'm going to add C to, again, eliminate y. Do two different equations, same variable to get rid of. So let's get B and C together. So B, once again, 2x minus y plus 2z equals 6. C is a negative x, a positive y, a positive 3z equal to 10. So if I put these together, y's cancel. That's what I wanted. 2 minus 1 leaves me an x. 2 and 3 gives me 5 in front of z. And then 6 and 10 is going to be 16. So now there's my resulting equation E. So now I'm down to, with D and E, a 2 by 2 system. This results in a 2 by 2 system. So I'm going to use elimination again. And I think the x is going to be easier to eliminate if I take equation E and multiply it by a negative 3. Then I'll have a negative 3 in front to cancel with the positive 3 here. So next, I'm going to take equation D and subtract 3 times equation E. Okay, D and then 3 times equation E, and this is to eliminate x. So equation D was 3x plus 3z equals 12. If I multiply this equation by a negative 3, then I get negative 3 in front of x, negative 15 in front of z, and then negative 48 after the equal sign. So if I put these together, x's cancel. 3 minus 15 is going to give me negative 12 in front of z. And then negative 48 and 12 combines to make a negative 36. And now I'm just about done. I can divide both sides by negative 12. And that gives me the first part of my solution. Z has to equal positive 3. So it's back substitution in here, or from here. So I found the solution for Z. Now I need to plug that into either D or E. So let's say I plug Z into, again, D or E. E looks a little easier for me, so I'm going to plug into E, although it doesn't matter if you use D or E. So we could have also said or D would have worked here. So plugging Z into E, we're going to have x plus 5 times z, which we just found was 3, that has to equal 16. So if x plus 15 has to equal 16, then x has to equal 1. So now I have x and z, so two of my solutions, and if I take those two, sorry, it's bugging me, that was not supposed to be pink. If I take those two solutions now and plug into A, B, or C, then I can find my last variable. So now I'm going to plug x and z into, doesn't matter which equation, but it looks like A is the simplest there, x plus y plus z equals 6. So I'm going to plug into A, although or B or C would have worked there. I'm going to plug into A. So equation A, again, says x plus y plus z equals 6. So x, which is 1, plus y, which we still don't know, plus z, which is 3, has to equal 6. Well, 1 and 3 makes 4. So if y plus 4 equals 6, then y has to equal 2. So my solution has x and y and z, so it's 1 and 2 and 3. So my solution is 1 and 2 and 3. X, y, and z. And again, if you wanted to verify that, you can plug 1, 2, and 3 in for x, y, and z into all three of those equations, and it's going to result in a true statement. Okay? Not brutal work. but it helps to be organized. And I'm sure some of these things you guys could do in fewer steps, like adding A and B together. You could probably do that in your head without having to rewrite them. Adding B and C together here, you could probably do in your head without having to rewrite. So if you can skip some of the steps, that's totally fine. But for me, what will happen is I'll get, down here to this step and I'll mess up a sign or something. And if I haven't organized my work, it's going to be really hard for me to find my mistake. And how would I know I made a mistake? Well, if I was doing one of these on, let's say, a quiz, I want to double check all of my work, I would actually plug the solution in to verify it. And in the verification process, I'd get a false statement somewhere knowing that I made a mistake. So if my work is organized, then it's easier for me to go back and find that mistake so that I don't have to just start from scratch, which sometimes you end up having to do anyway because it's tough, okay? So there it is. Those are consistent 3x3 systems. Generally what's going to happen when you solve a 3x3 is you're going to get your solution for each of your unknowns, but there will be those special cases. Remember, we can have an inconsistent system with no solution, and we can have a dependent system with an infinite number of solutions, and so I want to show you what those look like. So let's look at a couple of special cases. Now, at first glance, they might not look too special, but you're going to see the variables will cancel like they did with the 2x2s. So let's call this equation A, B, and C here. Let's add two of the equations together to eliminate a variable. So let's say we choose A and C. Let's add A and C to eliminate those x's. Okay, if A and C, if I go to add A and C together, what's going to happen is we're going to end up eliminating more than just an x. So negative 4x and 7y minus 3z equals 1. When I combine C, which is 4x minus 7y plus 3z equals 6, again, putting these together makes everything cancel on this side, so technically what's left is nothing. The number for nothing would be 0, and it's important to have that there so that we can interpret what's left, okay? On the other side, the 1 and the 6 is going to make 7. If I don't have the 0 there, it's a little hard to interpret, but here, variables cancel. That means they don't matter. It means no matter what you plug in for x and y and z, the result is going to be this, a false statement. So if the variables don't matter, if the resulting statement is always false, that means this is an inconsistent system. So this false statement tells you that this is inconsistent. So we can say that inconsistent, this is an inconsistent system, and so we can say that there is no solution here. Okay. Now if you just said it's inconsistent, that would be totally fine. All right, let's look at the other special case. Obviously, you know what's going to happen in this one, but just so you can see it, let's say we wanted to add A and B together. Okay, if we go to add A and B together, 2x minus 3y plus z equals 4, and then negative 2x positive 3y negative z equals negative 4. Well, this time, again, all the variables cancel, so you've got nothing left. But on the other side, 4 minus 4 gives you another 0. So 0 equals 0. Again, all the variables canceling means they don't matter. It means no matter what you plug in for x, y, and z, you're going to end up with a true statement every single time. So if the resulting statement is always true, that means you're going to have an infinite number of solutions here. So this true statement is telling you have a dependent system, and a dependent system has infinitely many solutions. So infinitely many solutions. Okay, now this process of elimination works for any size of a system. So if we had a 4x4 system, we would use elimination to get it down to a 3x3. And then if we had the resulting 3x3, we'd use elimination again to get it down to a 2x2. So no matter the size of the system, the goal is to use elimination to work it down to a 2x2. Okay? Now, if we look at this particular system, we don't have to go through all of that work. We've got 4 variables, we've got 4 equations, but if we look at the last equation, this is one where we could just use back substitution. This last equation if I just divide both sides by 11, I don't need to go through elimination. I can see the first part of my solution. W has to equal 2. And then I can take that 2 and plug it into the previous equation. So plugging into the previous equation, I have 3 times z plus 2 times w, which we just established was 2, that has to equal 1. So 3z plus 4 has to equal 1. So if I subtract that 4 over, 3z equals negative 3, and then divide, that means z has to equal negative 1. Now I can take the w and the z and plug into the third equation here. So let's see, 2y minus z, which is negative 1, minus w, which is 2, has to equal 9. So 2y plus 1 minus 2, that's 2y minus 1. So if I add that 1 over, then 2y equals 10, and divide by 2 means y has to equal 5. Well, now I can take all 3 of those and plug into our first equation. So we end up with, let's see, a negative x plus y, which is 5, plus z, which is negative 1, plus w, which is 2, and that has to equal 9 again. So negative x, 5 minus 1 is 4, 4 and 2 make 6. If I subtract that 6 over, then negative x has to equal 3. Dividing by negative means x equals negative 3. So back substitution works when our last equation is one step to solve, basically, right? If your last equation only contains one variable, that's what happened when we were solving the 3 by 3, got it down to a 2 by 2, got it down to something we could solve for that one variable, back substitution from there. So our solution is w, x, y, z. Nope, we're going to go in order of our equation, remember? So we want the x to be first, that's negative 3. And then the y, then the z, then the w. So y was 5, z was negative 1, w was 2. X, y, z, w, just like in the equations. Okay? So let me move this up a little bit. This is our solution for this system. Okay, now I don't think I'll be asking you to solve any 4x4s, maybe a good bonus question, but you would use the elimination process in the same way. Now, you may have been asking all along if this is something that Desmos could do for you. The answer is yes, but we have to be a little tricky about it. So yes, Desmos can do this, but we have to be tricky about it, and let me show you what I mean. So Desmos is a graphing calculator. It graphs in 2 dimensions, right? Graphs with x's and y's. As soon as you put a z in, it's not something that we can graph. So we're going to type our system in here. Okay, I'm going to show you. If we type in x plus, I got this next example, x plus y plus z, I've got to go to the keyboard to get that, equal to 2, nothing happens, because this is an x and y axis. There's no place for a third dimension, for a third variable for that z. So let's just keep going. Trust me for a second. So 3x minus y plus 4z is going to equal negative 9. And again, nothing happens. That's okay. Just keep going with me for a minute here. Then we got negative 2x, and then plus 5y, and then minus z is going to equal 25. Okay, so we're typed our equations in there. Now notice what happens at the end of the equations. It says to add slider. Now we don't want to do that every time, but we are going to tap add slider in the last one. And what that does is it picks a constant value for z. So if you see what's happening here, it's picked z equals 1, and that was pretty strategic there, but it picks a constant. If you put a constant in, let's say this equation, if you plug z in for 1, well, what's left is 3x minus 4y plus 4 equal to negative 9. Well, technically 3x minus 4y then would equal negative 13. That's a line. So that's why the blue one shows up. That blue line now shows up because z became a constant and now it's linear. And it did the same thing for the green one. If you plug the 1 in for z, then it could be added over and it creates that green line. And it did the same thing for the first one, okay? So it created 3 lines because z became a constant. And so what it's doing here is when it says add a slider, it means that you can, sorry, I messed up my slider. When you add the slider, if you actually hover on the circular part there, you can slide this around and put different values in for z. But the value we want is the one that it actually set for us, and it won't always do that, but we got lucky here. The value we want, oh my gosh, guys, my finger keeps messing this up. What we want is a value for z that makes all three of the lines that result connect. So it's going to guess at the value for z, and I can't, so I'm just going to type in the 1 there because I can't make it stop at 1. All right, so I got to try this again. There it is. Okay, so we are going to slide the value for z around until we get 3 lines that intersect, and where they intersect, that point is going to show you the x and the y value in the solution, and then the value for z is the z value in your solution. Okay, so after the last equation we type in, we're going to tap add the slider z, add slider z, and what that does is it guesses a value for z, but it's putting z in as a constant, making these three lines for us that we can actually graph. So what you want to do is move that slider around, if necessary, until all of the 3 lines intersect at the same point, and the point of intersection will contain the solutions for x and y, and the slider is going to show you the solution for z. So this is the situation you want here. You want all 3 lines to connect, or to intersect, I mean, at the same point, and so that gives you the solution. So you have -3, 4 is your intersection, and you have z equals 1. That means the solution for this system is going to be -3 for x, -4 for y, and then 1 for z. Was it -3? +4. Sorry, guys. You're probably like, you're messing it up. You're messing it up. +4. So -3, +4, and then 1 for z is going to be the solution. And now that we have a way to do this with Desmos, if we wanted to confirm, let's say we wanted to confirm number 1, not plug it in, then we could do that. So I'm going to cheat a little here so I don't have to type in all these variables again. So 3x plus y plus z equals 6, and then 3x minus 2y plus 2z equals 14, and then we had 3x and 3y minus 3z equal to -6. Okay, so see here, the slider's already there, right? But it's not, the 3 lines aren't intersecting, so you want to move the slider around until all 3 lines intersect, and you can actually get it to stop. I think we have it. So z equals 2, and x was 2, y was -2, z equals 2 was the solution we got, and there it is confirmed with Desmos. Okay, so Desmos can do this. It's kind of cheating, not in the fact that the calculator is doing the work for. I'm all for calculator doing the work for you, but what it's doing is it's guessing at a value for z, and you know, that's, I don't know if you consider it cheating, whatever. Some teachers don't like it, but I think if we have technology that will work for us, why not let it work for us, right? As long as we understand what we're doing with the technology. Okay, so there it is. Hopefully you got enough to get you going on the practice, but as always, just reach out if you need some extra help. All right, guys, take care.